get in here because, I mean, they are worried about our security, then please keep doing and keep posting your pictures. We have received some of them. Very, very interested. This one, what about this one?
Wow, this one, I love it.
I love it, from Kerelix.
Yes.
Company. It's awesome. They are showing their own robot. And this one from Dominic also.
Yes, so cool.
From Usarion.
So we have a lot of cool pictures.
Yes.
Wow,
And
another one.
Another one. Okay, that was very quick. Okay.
Well, but we're fine. They know we're fine.
Yeah, exactly. They know we are fine.
Okay. So yeah, now let's welcome our next keynote speaker, Jorge Nicho. Okay, so Jorge is a robotics research engineer from Southwest Research Institute.
Yes, and Jorge is going to talk about the MoveIt task Constructor, which is a tool that is used to generate a sequence of actions for robotic arms, and is very useful for robotics application, for industrial robotics applications. And so let's see, Jorge, are you ready?
Yes, I am. How you doing?
Perfect. Thank you very much. Then if you're ready, the audience is all yours.
All right. Great. Yeah, thank you everybody who's attending. It's really great to be part of this. So yeah, I'll go ahead and get started on my presentation. Okay. Let me see. Hopefully my screen is visible right now. So yes, as the introduction described, I am a research engineer at Southwest Research Institute. And today I'll be talking about how to sequence motion planning tasks using the MoveIt Task Constructor library. So this is an image of the application which you'll be playing with today in this presentation. And in this ROSDevDay, the kind of higher level goal is to take an existing motion planning implementation, and instead of using it, we'll be implementing our own MoveIt Task Constructor planner that will basically show you how to sequence a series of motion planning tasks. And using that, we'll be able to generate robot trajectories for this application. Okay, so more information about me. I joined Southwest Research Institute in 2011. Since then, I've been involved in development and deployment of many industrial robotic applications that combine various capabilities such as computer vision, 3D perception, motion planning, systems integration. And in the making of those projects, I've been able to leverage a number of open source libraries, including ROS, ROS2, MoveIt, the Point Cloud library, and OpenCV, as well as many others. So there are some links in there you can look at for some of the projects that are in the open source world, including this particular project. So you can click on those links and see more information about those. You can go into my GitHub links. There's my personal one and some of the other ones that I'm a part of, Swery Robotics for Southwest Research projects, and also some of the projects under the ROS Industrial Consortium umbrella. So about this project, so this is an application that we at Southwest Research Institute built a few years ago, where the goal of it was to explore how to make it easy to program robots. So as if you're familiar with robot programming, and now today's world, that it's somewhat of a time-consuming task. You have to enter each individual motion line into the program, right? And that requires many hours of training, and usually the crafting of the program itself, it takes a long time as well. So, right? So we wanted to investigate how to make that easier and avoid having to do all of that work. And so the goal of it was to, one, simplify the task of industrial robot programming, then also look at effective ways to enable human to robot collaboration, right? Since that's something that's becoming more predominant nowadays, we want robots and humans to work together and kind of leverage each other in some meaningful way. And then also investigate hardware that would be appropriate for a collaborative robotic system. So this application was actually built was built in our facility, and it was comprised of the following components. So we had an industrial KUKA IWA arm, which is a 7 degree of freedom robot. And it has this compliance feature where you're able to drag it around by hand, right? So that makes it very easy to use. It also had a real sense camera mounted on the robot. You can kind of see in the picture there where the camera is, a small camera. It's a color and depth camera. We also had an Intel NUC PC, so it's a small computer unit which was sufficient to run this application. We had a USB joystick which allowed the operator to interact with the application, and also a custom-made handheld wand. So you can see there the object that is being held by the hand is this wand, right? It has these AR markers placed around in the surfaces of the box. So one of the highlights of this application was the tracking capability. So the camera was basically taking images, and then those images were being sent or published to a ROS node that was tracking the location of the AR tags. And by resolving where each tag was placed, it would then tell you the location of the wand. So we would use that location to then send motion commands to the robot. So some of the details of this software is that it was built as a ROS application, ROS1. It's comprised of a state machine, which is the main application, right? It's making all the high-level decisions. There's a tracking node, which I mentioned just now, and it tracks the location of the wand. This is only on the physical system, obviously, because in this particular project or talk, we don't have a real system. We'll just be using a simulated version of this. So you'll see, I'll show you later what the simulated version of this looks like. There's an input node, which tracks the commands entered through a joystick when that's available, or if not, then we'll just use a keyboard. But the joystick is a preferable method as it makes the application much easier to use. The motion planning node is the one node that plans all the robot trajectories, and this is the node that we'll be looking or working with today in order to show how we use the MoveIt task constructor library. And there were obviously a bunch of other nodes, camera drivers, robot drivers, RViz, obviously, and some other support nodes. This application can run entirely in simulation mode, so you can pass some flags and have it run in simulation. You can access the entire project in GitHub, and there's also installation instructions for you to be able to download dependencies and then compile the entire project in your own machine. So having said that, we'll now go to the fun part, which is where we run the application. So this application in particular is comprised of two launch files. There's one that brings up most of the nodes, including the main state machine node and RViz and all most of the visualization things. And the second one is a launch file that brings the planner node, the motion planner node, as well as the input node, which in this case will be using the keyboard since we don't have a joystick available for this project. So with that, let me go ahead and run things. We're going to change tabs now, or actually bring up the terminals. So here I have two terminals. So they got disconnected because I hadn't used them in a while. So I'm going to just clear the screen to start fresh. So now I'm going to copy and paste the first launch command. Okay, so I'm going to run that. It's going to take a little while to come up. Okay, so now, unless you see an error, you don't have to do anything. But if you see an error, which in some cases happens, just kill the node and restart it again. But now it should have brought up some visualization. So we'll go to the visualization window. So we'll see the first thing that comes up is RViz. So this is basically the robot environment that we have, right? So it's just a KUKA robot and on a table. And you don't have to pay attention to this widget here. It was used at one point in the application, but it's not really used in this particular project as it is right now. So there's the robot at some position. And now the other window you have to pay attention to is this TF Publisher slider widget. So we're going to expand it a little bit to make it easier to use. But basically, since we don't have a real wand and a real camera to track the wand, instead we'll be using this window to move the wand around. So if I move in the X direction, then you'll see the wand being moved in that direction, and that robot is tracking that location and moving with it if it can, right? So you'll see it, and you can change, the X, Y, and Z coordinates, and it'll update the location of the one accordingly. You can also change the rotation, roll, rotation about the X-axis, pitch about Y and Z. We'll mostly be using the X, Y, and Z sliders, as it makes it easier for the robot to find an inverse kinematic solution to that location. But one thing you should know is that if you keep moving too far from the robot, eventually it'll turn red, which indicates to the user that that pose is unachievable by the robot. It's too far, or it cannot reach it for some reason. So, then you have to get closer again, and then the robot will turn back to its normal orange color to tell you that that pose is a valid pose. So that's basically it for now with the visualization aspects of this application. So let's go back now to our terminal window. So let's open up another terminal, and this terminal disconnected for me too. So I'm going to clear the screen again. Okay, so I'm going to run the second launch command. I'm just going to copy and paste into it. Okay, so we didn't see any errors, so that's good. So let's go back to our visualization. So the only other thing that comes up right now, or the two things that come up, is this menu, right? You will see a menu of possible commands you can give to the application, and then this keyboard window. So because we don't have a joystick, then we're using the keyboard option, but that's a little tricky because it requires you to be in the keyboard window to be able to actuate the application with the keyboard. So once you're in the keyboard window, make sure you click it at least once. You can then move through the menu. And it's not working for me. Okay, let me try that again. Somehow it's not working. Okay. No, I'm still not letting me move. Okay. Okay, let me try restarting the whole thing again.
Hey, Jorge, maybe
yes.
You can try to open not in another tab. Maybe, I don't know. I don't think that this is the case. I mean the simulation. Yes, put it as another window here, so you can close it and reopen it again here.
Okay, this whole window?
Yeah, the whole window of the, yeah, exactly. Okay. I don't think it's this, but just in case.
Sure.
So you can go now and open again on the icons below.
Okay. Okay, let me get that going. Okay, so now I'm going to launch the second node. Okay, great. It's working now. Yep, that was it. Somehow that made it get confused. Okay, so now we have all of our window elements here, right? So as I said, you have to be in the keyboard window to move with the keyboard. So in order to move up, you press Q. To move down, you press C. And then to accept or issue a command, you press A, right? So all of the keys are pretty close together. So let's say I wanted to teach a waypoint to the robot, right? So let's go ahead and teach the point where the one currently is at. So for that, we'll go into the add waypoint and then press A, and you see it added a red dot in there. So that means it's taught this waypoint, right? So in the real application, what would happen instead is the human operator would move this wand with his hand in space, and I don't know what happened. Just a second, let me log in. Somehow it kicked me out. Apologize for the little technical error there.
Yeah, no problem, Jorge. So let's take it easy and take our time.
Yep. Okay, let me display the graphical tools again. See if I can go to a different tab.
Yeah,
okay, great.
I recommend you to close all the other tabs that you are not using for the same project.
Okay, I think I only have, well, I'm going to close this one and I'll open it later. All right, so I had taught one waypoint. Let's say I want to teach a second one. So I'm going to move slightly in the Y direction. And now I'll press A again. So now I taught another waypoint. So let's say I want to move up slightly. Then again, press A to teach another waypoint. So I have 3 waypoints. But I can also add a segment, meaning a sequence of waypoints, right? So instead of just adding that, I'll go to the add segment command and then accept that. And then now what I can do is I can move the robot and now you'll see creating a yellow line. That means it's creating a sequence of waypoints that follow that path, right? And as I was saying, in the real world, a human operator would be moving the wand and the camera would be tracking it. So it would then, use the movements of the wand in that case to teach the waypoints. And, you get more organically looking trajectories. But because we don't have that at the moment, we're just relying on this slider window to create those. So anyway, now that we have enough waypoints and a segment, we'll go ahead and generate a motion plan to move through all of those. So we'll go into the preview path command. And then what the application will do is we'll call the trajectory planner node and ask for it to plan for all of those waypoints and segments. And now you saw that it executed the entire trajectory for that robot, right? So that was only a preview. So in the real application, you would see that preview, and then the user could verify that the trajectory is good and every waypoint is reachable, and then no strange motions took place, right? And then once you verify that, then you can execute the path. In this case, it would execute it in the actual robot itself. In this case, we have a simulated real robot, so it's using that robot instead. But you can see the execution of the path, right? So that's the main way in which this application works. Then you can delete all the waypoints if you select clear waypoints. Don't mind the change snap mode. That was another feature that is probably not enabled at the moment. But this is how we created or set up this application to where the user was able to very easily create waypoints and trajectories that the robot could then follow. So going back to our notebook. Okay, so I just described how to run the application. So whenever we created a toolpath and then we requested for a preview, what the application is doing internally is sending a service request. So if you're familiar with how services are handled, you have to have a service definition somewhere, right? And that service definition has some specific things. One of those is the request area where you pass all the information that is necessary for the server to be able to service that request. In this case, this is sort of what is in that service definition. So the important part of this definition is this trajectory segments field. So this is nothing more than an array of things. And what this array contains is the waypoints and segments that we taught to the application. So that information will be sent to the planner server through this field. So this is sort of what's in the trajectory segments field, this trajectory waypoint array. So this waypoint array is a collection of waypoints, obviously, but then each waypoint is nothing more than an X, Y, Z, and a roll, pitch, and yaw value. So one thing that the application checks whenever it receives a trajectory segment to plan for is whether it has one waypoint or more waypoints, because it uses that information in order to determine whether it needs to do either a free space motion plan to one waypoint goal, or if it has to follow a sequence of waypoints. So those two cases are handled differently. So in the original implementation that we had a while back, we implemented this trajectory planner class, which is is what does all of the planning work to generate a robot trajectory. So it provides a plan method, and we'll be looking at this in a little bit. It provides a plan method, and it uses the move group planning interface to generate most of the motion plans. So if you have used MoveIt in the past, you'll know that in order to do motion planning, you have to have a move group interface class in order to do motion planning functions inside your application. So some of the downsides of this code is that it's not very easy to read, and that's sort of my fault because I wrote the code, so it wasn't the best implementation at the time. And it needs to do a lot of bookkeeping in order to pass the starting state every time it needs to plan for either a new segment or a waypoint. So you can, in your own time, look at that code to understand how it works, right? But now we're going to inspect that code very quickly just to get an idea of how that looks and how that original implementation was made. So we go into the Catco workspace, source directory, expand this a little bit to expose the names more clearly see them. Then in the visual programming, which is the repository that we're working with, you go into VPR trajectory. VPR stands for Visual Programming Robotic, or something along those lines. And in there, you'll go into the first node that you interact with is this trajectory planner node, right? So this is a very simple ROS node. It has a main function, and then all the usual ROS initialization stuff that you have to have for an application to be considered a ROS node. You have your spinner, you have to load your robot model here, as you can see, right? This is very common stuff that goes into a ROS MoveIt application. And then we have this task planner line, right? So this is where we instantiate or create an object of the planner class. So this planner type is just an alias. If you go up here in this line, you'll see that this planner type is commented out now, but it used to be this trajectory planner class. And now it's been replaced with the MTC planner, which is the class that we'll be inspecting in a little bit. But this trajectory planner is the original implementation, which has been replaced by the MoveIt task constructor planner. After that, there's just a service callback. So as you know, when you implement a ROS service server, you have to have a callback that handles the requests that came from a client, right? So the callback definition is here. So it's very simple. It takes a request argument and a response, and then it just calls the planner internally with the request data, and then it returns a robot trajectory in this variable here, and then you get a success flag. So that's all that it goes into this planner node. But then the trajectory planner node is what actually does the planning, and we won't go into the source file, but let's just look at the header very briefly just to see what goes in there. So this trajectory planner, like I said, this is the original implementation, has this form, has this is the public method that applications from the outside will be interacting with. So it takes a request in a trajectory as an output. So basically the request has all the information needed to generate robot trajectories, and then the result is put into this trajectory variable. So our MoveIt task constructor implementation that will be replacing this has to have the same function, but obviously the implementation details of that function will be different. Like I said, you can look at the source file for this class at one point at your own time to understand how that was implemented. Okay, so now let's go back to our notebook. Okay, so the objectives of this is to implement a MoveIt task constructor planner class that implements that public method we just saw, right? We'll replace the trajectory planner class with the MoveIt task constructor planner implementation, learn MoveIt task constructor classes such as task and stages and what they do and how they interact with each other. So tasks and stages in particular are the main components of the MoveIt task constructor and how you assemble a task or a job in this library. And then you'll implement your own MoveIt task constructor stage to plan for an array of waypoints or for a Cartesian trajectory. So some background on the MoveIt Task Constructor library. You can go into this link and you'll find documentation on that, all the documentation that is currently available for it. You can see there some basic concepts, how it works. And, there's a lot of good information there. So feel free to visit that page when you get a chance. But in essence, it is a framework that provides a flexible and transparent way to define multiple interdependent planning subtasks. So it draws on the planning capabilities of MoveIt. So MoveIt already by itself has a number of planning capabilities to generate motion plans, to solve IK, to generate grass posts. So it leverages all of that in order to solve common planning problems in a sort of black box planning stage. One thing about the way it works is that the solution produced by one stage, so a stage is a component that generates a solution for a specific job, right? And once it solves that job, then it passes its solution forward so that the next stage knows where to begin. And so each stage passes its own solution to the next one in the form of a planning scene. So if you used MoveIt before, the state of the environment, a robot environment, is captured in this planning scene. So that planning scene has all of the information about where the robot currently is, all the objects in the environment, and so on. So all of the low-level work is done inside the stages, and a task is sort of a container for all of the stages. So if you created a number of stages, each one doing different things, then you have to put those stages in a task. And the task will then, depending on how the task is configured, we'll call it in a specific sequence, right? So you can have a sequential task or a parallel task. And for this application, we're just using the sequential version, which is the simpler one, but you can also have parallel compositions if that's what your application needs. So in the MPC library, there already exists a number of stages that you can use very easily to do motion planning through a robot goal, setting the current state, generating the grass poses, pick and place, motion planning, or computing IK, and many others. So for this application, we'll be using the first two, the planning to a robot goal and also setting the current state. So this chart here sort of shows more or less the depiction of our application's MoveIt Task Constructor task, right? So there is the task, which we call VPR task. And then this task contains these stages. There's one at the beginning called start state, which sets the state for the planning environment. And then there are these stages. Each one plans for, the trajectory for either a single waypoint or for a sequence of waypoints or a Cartesian toolpath. Okay, so now we'll go into the implementation of the MoveIt Task Constructor class. So let's go ahead and look. Well, before that, I'll just say that some of the methods here, all of the methods have been implemented. So we'll just go over the more important ones, which are the plan method, then the create free space plan stage method, and then create toolpath stage method. So let's go ahead and take a look at that. Okay, so let's go ahead and go into the MTC planner. So this class is what replaces the original implementation, right? Obviously, it has a constructor and destructor as part of the norm for C++ classes. But then we see again that this plan method is also implemented here, right? It has the same function signature, same arguments, everything is the same, but the implementation, though, as we'll see in a little bit, is different. It also has these other protected methods. So these methods are not accessible outside the class, but will be used to create the various stages that we'll be using to create the MoveIt task. And then there's this lookup transform. This is just a utility function that does TF lookups. If you've ever dealt with ROS environments, you know that TF is how ROS knows where things are in the environment. So now we'll go into the source file for this very quickly and take a look at the implementation details. So there's obviously the constructor, and we don't do much here other than initialize a scene monitor. So a scene monitor is an object in MoveIt that allows you to get the current state of the planning scene, right? So checks for the environment and grabs all of the information about the environment and holds it inside your application. Then the next important method that we need to look at is the plan method. So the first line here that we see is we create the MoveIt task, right? So this is how you create a task. So you specify the type of container. In this case, we want a serial container. And then we have to do some initialization with it, like load the robot model and enable introspection. So this is used for visualization, so you don't have to worry too much about it. Okay, so now that we have a task, then we can create stages that will then insert into our task in a specified order. So the first stage that we create is this create fixed state stage. So all this does is it creates the initial state of the planning environment. So you can later look at that method on your own time to see how that is done. But basically all it does is it sets the initial state of the planning environment. So you always need to have that in an application like this. So then once we have the stage, we insert it into the task. And this is the syntax for how to insert a stage into a task, right? So that makes it effectively the first stage in the task. So now what we're going to do is we're going to loop to the request that we got from the main application and loop over the segments that were sent to us. And so one of the things that we do is we first check at the size of the waypoints array in this segment. So if the size is just 1, that means there's only one waypoint in this segment. But if that's not the case, that means there's more waypoints, then we handle it differently. So if there's only one waypoint, what we do is we create a stage that creates a plan to a single waypoint, right? So this is the function that does that, and we'll take a look at it in a little bit. But we pass some variables to it, and it gives us back a stage. Then the next thing we do is, if the waypoint or the segment has more than one waypoint, then we create a different stage that handles a sequence of waypoints or a Cartesian toolpath, right? So that means it has to move and follow a sequence. And so that gives us a different stage. So once we exit out of the for loop, we insert the stage into the task, right? So as you can see, the order here is dictated by the order of the trajectory segment. So we'll continue to insert stages until we complete all of the different segments. And once we have a stage that is populated with stages, we just call the plan method. So it makes it very simple, right? You just insert your stages and you call the plan method, and then you check if it succeeded or not. And everything that happens here is more for publishing, visualization things, and just returning a solution in the right data type back to the server or to the client that called the server. So, but we've already seen the kind of the key pieces of this plan method implementation. So the next function or method that is important here is this create free space plan stage. So basically, what we're doing here is we create a free space planner or a pipeline planner first, and then we pass that planner into this move to stage. So this is one of the stages that is currently available within the MoveIt task constructor library. So you can easily use that. All you have to do is pass it a pipeline planner, provide some parameters. You have to set some properties for it, and then you return it back to the main plan node, and that's how you create it. For the other one, where we have to handle a sequence of waypoints or a Cartesian toolpath, what we did is we implemented our own stage. So this is our own implementation, which we'll look at in a little bit. But basically, we create a stage, and then we set some properties for the stage. These properties are used for, controlling how the trajectory planning goes. And at the end, you can sort of look over this. All it's doing is creating a toolpath or converting the toolpath into the right data type. But in the end, what we do is we pass the toolpath that we want to plan for into the stage. And then once we have the stage ready, we return it back to the plan method. So those are the main sort of methods that we need to look at in this class. So now let's go back to the notebook. Okay, so So we've looked at the plan method and the various important methods. So the next thing we need to do is as I mentioned, we implemented our own stage for handling the case of a sequence of waypoints, right? So the MoveIt task constructor already gives you that move to stage that you can use to plan to move to a single waypoint. But since there isn't one to plan for a sequence of waypoints, then we have to implement our own, right? And we'll look at how we do that now. So go back to the code editor. We'll go into the include directory and open the plan toolpath header file. Okay, so this is our stage implementation. So if you've ever dealt with inheritance in C++, you can recognize this syntax where it basically says that our implementation will be inheriting from this propagating either way class, right? So inheritance means in this context that we'll be implementing methods that this class has. So this class provides a number of methods that we need to implement in our own implementation, right? So those methods in particular are init, compute forward, and compute backward. So you can recognize those by the override. Usually, well, the keyword override means you'll be overriding an existing method that was given or provided to you by the base class. So if you ever need to implement your own planning class, you will derive from this propagating either way class. So those are the methods that we're using or that we're inheriting from the class. And now we'll go into the source file to look at the actual implementation of those. And so now we have our constructor, obviously. And all we do here in the constructor is we declare some properties that our stage will need, right? So group name, the name of the arm, which contains the information about the kinematics of the arm itself. Obviously the toolpath, because we need the toolpath to plan for it. And then some additional parameters, which are optional, that are used to control how the motion planning goes. So properties are the usual way in which you pass information into stages. So at one point, I invite you to look at that and see how you declare properties. You have to declare the name and the type of the properties. But this is how you basically set up information that needs to be passed into the stage. Then the other method that's important that we need to look at is this init function. So the one thing to highlight here is that you have to call the init method of the base class, right? So in this case, the propagating either way class, which is the base class, it has an init method as well. So we need to call it and pass the robot model to it. If you don't do this, then your application may actually crash or not work. So it's important to remember this. The rest of it is just some error checking. So no need to be too concerned with that. The next important method here is the compute forward method. So the compute forward is where we actually do all of the work of generating the motion plan for our toolpath. So the first thing we do is we grab the properties and we collect the properties that we need, all of the information that is needed to generate the motion plan. So all of that is happening up until here. Then here, what we do in start scene, we get the current state of the planning scene, right? So this line is grabbing where the scene currently is, so which was passed to us from the previous stage in this from variable, right? So from contains the current state of the environment. So once we have that, we move to where we actually do the planning. And so it's this line here. So what we do is we just call this compute Cartesian path method, right? This method generates the trajectory for you. So you just call it and pass the variables that it requires, right? The information about your robot model, the tool link name, all that stuff, including the toolpath itself, right? So once you call the method, then it gives you this double number. So the reason why you get that number is because you can check whether the planner was able to generate a valid trajectory for all of the waypoints or only a fraction of them. So if it's less than 1, that means it was not able to plan for all of the waypoints. But if it's 1, then it means it fully succeeded. So you check that here. If we fail, then we issue a silent failure. But if not, we continue. Then after that, all we do is we collect the robot trajectories and put them in the right variable to then return to our main application. And so that's all that takes place here. So we're just converting between data types to a data type that we need to return. And one thing to take note here is that, as I mentioned earlier, each stage passes its solution forward to the next stage, right? So the way that we do that here is by using this send forward method. So essentially, what this send forward method is saying is, in order to get from the initial state to the final state of the environment, we need this trajectory to get us from one to the other. So that's all it's saying, right? That's how you interpret this line. So and that is it for this implementation. I would invite you to go over this code at one point to understand it better. But in summary, what we did basically is we have our main node, which has a service, and the service calls this planner. Now our planner is a MoveIt task constructor planner, right, which implements this plan method where we handle the case of planning for a single waypoint or a toolpath, meaning a series of waypoints that need to be followed by the robot. And then in order to plan for a series of waypoints, then we implemented our own MoveIt stage that handles the case of planning for consecutive waypoints, right? And that's how we handle that here in this compute forward method. One thing that I forgot to mention is that we also had to override this compute backward method. But since we're not really using it in this application, then we just sort of automatically issue a failure if it gets called, right? So I believe this function is used for the case where you want to plan backwards, which this application doesn't need. But if your application ever needed it, then you would implement this method for that.
2 minutes.
Sure. Okay, so now I'll just rerun my application here. Actually, I won't be rerunning it since it's already up. One thing I will show, though, is the visualization here. So I'll expand the display panel, and now what I'll do is again, and my keyboard's not working. Okay. I guess I'm gonna have to go back here, open the visualization again. Okay, great. And so the view resetted itself. So let me drag it real quick. Okay, so now when I go and request a plan preview for the same trajectory that we had, you'll see the MoveIt planning task stepping through all of the different stages that it has, right? And so this is very useful to have, as it'll give you details as to what the system is doing as it's planning for things. So that's kind of the visualization that you get with the MoveIt task constructor library. So it's very handy, especially for larger projects or larger applications that have very complex structures. Then this will help you understand the workflow of that application. So with that, that's the end of my presentation. Hope you all enjoyed it. And yeah, thank you for attending.
Thank you very much, Jorge.
Yep.
Thank you very much. And then now it's time that we go to the questions. And we already have some very interesting questions on the chat, on the questions tab in the panel of the conference. And let me go with this one. It's not the first one, but let me start with this one. It's a question from Anuba Dogra. And he's asking, is it possible to add multiple waypoints through MoveIt Python interface such that it follows continuous velocity for all the points rather than following a trapezoidal trajectory between each waypoint?
So I believe MoveIt, as of now, has a capability to plan for a sequence of waypoints. So that's what I leverage in my application. Mm-hmm. However, I don't think it forces a constant velocity on the trajectory. So it might try and stay or keep a specific velocity, but it won't necessarily if it needs to deviate in order to follow the path, it will do that.
Yep. Okay, makes sense. Then I have another question here, very interesting, which is from Nitin Diman. And he says, if MoveIt has been used for, or you have been using for multi-arm planning and avoiding collision between the arms. So because sometimes the sensors of one arm can block the sensors of the other and prevent from detecting some obstacles. So have you tried this in any of your configurations, and what can you tell us about it?
So that's usually a very tricky problem, right? The problem where you have two robot arms and they're trying to simultaneously do something and avoid colliding with each other. So as far as I know, when MoveIt plans for something, it takes a snapshot of the planning scene. And whatever the snapshot capture at that point is what is used to reason about collisions, right? But if things are moving as you're planning, then the motion planner is not going to know that. So it'll assume that things are static while it's planning. So when you have a situation like that, I would recommend to, make sure that you sequence your actions in such a way where collisions are minimized.
Okay. Then I think that many of the questions are more related to MoveIt itself than rather to the task constructor here.
Right.
And then let me ask you another one which is actually the most voted one by Meg Rob. And then if is MoveIt mainly designed to be used for manipulators, right? But can it be used for other types of robots, such drones or ground mobile robots?
I believe you can. It basically uses the kinematics of your robot, right? So if your kinematic is set up in such a way where it represents your mobile robot, in this case, as a series of linear joints, then in theory, it is possible to use it for planning for such robots rather than manipulator arms. Although it's very good at planning for manipulator arms, I think it's the way it's been built is general enough to where you may be able to use it for a mobile robot or a drone even.
Yes, we have used it actually for planning a drone navigation in an environment with some obstacles. And you can use the planner because it's a very good planner in 3D, and then you can put the constraints of the obstacles that are around. But as you mentioned, this has to be with the obstacles static. If they are dynamic, then that's another thing. That's another problem. Then let me ask you one question myself. So we talk, so we know each other for another conversation and actually an interview, and you were explaining me about the real life application of your software that you develop for industry using ROS2, a bridge between a ROS1 and ROS2, and then you mix everything into a single application for a real robot. And have you, my question is related to that, have you used the MoveIt Task Planners in order to build any real-life robot application?
Yes, I have. In fact, that was how I learned about the Move Task Constructor, because I needed to, it was a rather complex sequence of actions that I needed to handle, and I wanted to have flexibility in how I handle those actions. And in looking for frameworks that would allow me to do that, I ran into the MoveIt Task Constructor. Actually, I had known about it. I never had a chance to use it, but after inspecting the code, I realized that it was very fitting of my use case, and so I decided to use it for that. And then once I learned it, I was able to implement the type of flexibility that I needed to handle, the complexity of my application. So yes, unfortunately, I cannot go into further details in that application.
Okay, that was my question, more interesting part, but I had to understand. Just to let you know that when you started the presentation, then there was a comment on the chat. Somebody was very excited about your presentation and saying, "Whoa, this is going to be very good for real life applications because we are going to increase a lot our productivity on developing applications for industrial robots."
That's great.
Great. Okay, so thank you very much, Jorge. That's all for today, and see you around the universe.
Yep, excellent. Thanks for having me. I appreciate it.